Good afternoon, everyone. Today I am going to introduce myself on the N-oxidation, catalytic N-oxidation over platinum-based catalysts for the hybrid process SCR process. The question arises, what is it for hybrid process SCR? Going to the next slide and the hybrid process SCR process consists of two reactors. One having oxidation reactor and one having SCR. In that process, hybrid process SCR, simultaneous oxidation and reduction take place. Actually, there are this process is used for the removal of NOx, and there are other processes low SCR and standard SCR. But this process is much better at low temperature, and it converts. In this, the objective of this is, in the first reactor, we convert NO into NO2 in order to make it in equal molar quantities. Then this equal molar quantity is treated with ammonia or any containing urea or like this to convert it into nitrogen. This process is for a very low temperature and very high mass. Actually, I am dealing about the oxidation of NO, so I discuss about the mechanism which it follows. There are such kind of two kinds of mechanisms. One is aerated mechanism and one is Henschel mechanism. This mechanism follow in this platinum. This oxygen is absorbed on the platinum dissociatively on the platinum, and this absorbed platinum, then NO treated with absorbed platinum, this oxygen react with and produce NO2. This process equal depending on thermodynamic equilibrium. At some level, at some high temperature, it reverses. It is a reversible process, and again NO2 converted into NO2. So this is, if the particle size is bigger, then actually the platinum oxide is formed. So if particle size is bigger, then it will not form. Less platinum oxide will form. That is better to give high conversion. These are my overall objectives dealing with different parameters about the SO2 and CO oxidation. Also the N oxidation and the effect of CO and SO2 and all the SO2 poisoning, all things. But the basic concept, basic idea, basic objective is to produce NO2 for the hybrid process SCR process. This is the schematic flow sheet diagram for on which I work. So in this one is a reactor from the 8 mm diameter, and thermocouple, saturator, and mosquito analyzers, condenser, and we maintain the temperature 42 so that no condensation takes place, and the emergency controllers, and heat jacket, and water catalysts I use, different SVs and different SVs, and we use NDI analyzers, different, and the effect of CO, SO2, all these on these. Separating variables I used for these. This is the N oxidation. I use different water concentration, different oxygen concentration, different NO, different NO2, different temperature variation, and space velocity variation, and the NO, effect of NO and NO2 also. And for CO, I use different temperature, effect of CO and effect of NO. Of these, I use also different for SO2 oxidation. I use also for different catalysts, platinum impregnated on titanium, anataya and rutile, and aluminum. These results show the effect of SO2 on these different catalysts. I have platinum titanium, but it contains tungsten oxide, so that it phase transformation will not take place. And this is rutile and another alumina. And this is the effect of, did you see that? And this we find that another show good results because the stability of sulfate is less on the NSIR, but rutile shows remarkable less conversion, very bad in the presence of sulfate formation. And also alumina decrease because aluminum sulfate is found. These graphs show the oxidation of NO in the presence of different oxygen concentration. When the concentration of an oxygen is low, then it shows low conversion. But at the concentration of oxygen is high, then it gives good conversion. But at certain limit, after that it levels off. No more because the platinum active site becomes saturated with oxygen. So that's why in this case NSIR gives good conversion and rutile gives little bit low. You see that 10% and 12% almost nearly same. But initially 3% very less, 10% very high. So that is the effect of oxygen. These are the different assays which I performed for the N oxidation. One is 60,000, 100,000, 150,000, 200,000. And these, as you know already, everybody knows that if we decrease NO conversion decreases with the increase in space chemistry. This I mostly use 150 ppm. And this is the effect of NO concentration on NO conversion. With the NO, if we increase and low oxygen, NO concentration gives high conversion, and with the increase of NO concentration, it decreases because there are two possibilities. One is NO direct from adsorbed state, then the competition between oxygen and takes place. And if it's direct from gas state, so it is different. But oxygen is reacting from adsorbed state and NO reacting from gas state, so it gives in low conversion. NO2 is also gives, in the presence of NO2, it also gives low conversion. One thing is that you see that one thing is thermodynamic equivalence earlier, and the second thing is the platinum dioxide is formed, so it decreases mostly on the NO conversion most decrease. And the effect of SO2 on the NO conversion, if we increase, because I already explained that if we increase the sulfate of SO2, then the conversion will decrease simultaneously with the increase of SO2. This is the effect of water. I put water concentration 8% and 0%. The presence of water decreases the efficiency of because it is absorption turbulence and decreases the activity of the catalyst, and hence the conversion is also decreased. This is 3D diagram for the oxidation. In order to show you at what point the maximum conversion. Did you see that at 60,000 aluminum and at 350 we see this point is the 60,000 350 gives the highest conversion of all. And this graph summarizes all the parameters behind this. This is C oxidation over different catalysts. You see that I use 500 ppm CO as in the gas, and you see mostly almost all catalysts gives same conversion, a little bit very less difference on these catalysts, and we find it gives as previous case it gives good conversion. This is the effect of CO concentration on CO. If we increase the CO concentration, then it gives a conversion at high temperature, as compared to the others. As as I calculate the partial pressure, if the partial pressure of CO is higher than the oxygen, then it gives its Lenz's-Henschel mechanism. And if the partial pressure is low, then it follows the Earle-Rodin mechanism. In this, CO and O both are in resolved state and they and to form CO2. And is only CO in gas state and O is in the resolved state. The partial pressure of CO is higher, then it preferentially absorbed on the catalyst. So it covers all the active sites. So that's why if it's increased, then that's why a high concentration of CO it gives high conversion. This is the effect of CO on the SO2, on the CO conversion, effect of NO on. At low temperature, NO is not converted to NO2 because NO2 is an oxidizing agent. So at low temperature it is not oxidized, but at little difference on mostly all, and also NO absorbed on the catalyst. So there is competition between the CO and NO. That's why it gives low conversion. In the presence of NO, the CO conversion decreases. And this is the effect of NO on SO2. As we know that NO2 is oxidizing agent. So when the NO conversion takes place, then the SO2 oxygen also increases because NO2, as we know in the contact process, we use as a catalyst. NO2 is used for the oxidizing agent to increase the SO2 oxidation. So that is the phenomenon takes place in this. These are the conclusions. Let's say, in order to conclude all these things, this catalyst gives a higher conversion, rest of these, and the oxidation rate depends on oxygen concentration, but it levels off at high concentration of oxygen, and increasing of NO oxygen, NO concentration, the NO2 decrease. Greater the SC, lesser the conversion. The presence of NO2 also decreases the NO concentration, and the presence of water also decreases the NO oxidation. And another because another catalysts are not much affected by SO2, but high affected much less surface stability. And the SO2 oxidation increases in the presence of NO, but NO oxidation decreases in the presence of